Hi there. If you play chess, you'll probably recognize the following moves as illegal. In the top row, pawns move 2 squares at a time while they are not on their home row. In the bottom row, you'll see a pawn moving backwards and another one moving sidewards even. So in classical chess, these moves are illegal, but there are variants of chess where these moves aren't illegal, where they are actually explicitly part of the rules. These are alternate chess rules, and this paper is about exploring those rules. What happens if you implement those rules? How does the gameplay change? And what can we learn for general games? So the paper here is called Assessing Game Balance with AlphaZero, Exploring Alternative Rule Sets in Chess by Nenad Tomasev, Ulrich Paquette, Demis Hassabis, and Vladimir Kramnik, the former three of DeepMind, and the latter was the world chess champion for these 8 years depicted. So the paper tries to bring together two different worlds. First, it is the chess world. So a lot of this paper is explicitly about the game of chess. If you don't play chess, or if you occasionally play chess, like myself, this might not be the most interesting paper, though it contains some really interesting kind of bits. The other world is the reinforcement learning world, which you'll see in the AlphaZero name right here. So the reasoning behind this is the following. Chess is a really, really old game, and rules have evolved over time and have sort of consolidated on the rules we have today. But also strategy has evolved over time, and lots of thinking and theory has gone into the strategy of chess. And to change the rules around, you can change the rules of chess. However, you can't really assess how the game would be played by humans if the rules were changed, because you don't have 1,000 years of the entire humanity studying these new rule sets, and therefore you're kind of stuck with assessing the games from the perspective of someone who has learned the old rules. But reinforcement learning to the rescue. So consider the following rule changes. No castling. This is a really simple rule change. No castling. Castling is disallowed throughout the game. If you don't know what castling is like a special move where there's this rook and the king is right here. I don't know how to the king. And if there's nothing in between, they can sort of swap positions. It's called castling. It's a special move that you can do, and it allows you to bring the king to the outside where the king is safe, and to bring the rook to the inside where it can potentially cause a lot of damage. So it's a very, very favored move by a lot of players. And no castling, the rule change, probably alters the game a lot, because if you think of the chessboard, kings start about here. They can only move 1 square at a time. So to get them to safety will require like 4 or 5 steps for them, while you have to move everything else out of the way, including the rook that stands here. So players might elect to just leave their kings where they are, but then they can't really open up in the middle as much, because that would leave their kings exposed. So it is fair to assume that just introducing this one rule might change the games around quite a bit, how the game is played. But as we said, we don't know. This is from someone who has learned classic chess, and all the grandmasters that we have played and learned classic chess. So how do we assess this? This paper says that AlphaZero can be used to assess these new rules. So AlphaZero is a reinforcement learning algorithm that can learn these board games very, very quickly, within 1 day or so. And it can learn them so well, it can beat humans at the game easily. In fact, modern grandmasters and so on use these algorithms in order to learn and to better their play, in order to expand their theory, their knowledge of the game, to play better against other humans. So AlphaZero, imagine AlphaZero can solve a game to perfection. what we could do is we could simply give this rule to AlphaZero together with all the other chess rules, and then let AlphaZero solve the game, give it a day and 50 billion GPUs, solve the game to perfection, and then look at what AlphaZero came up with. Kind of look at the games, how they turn out, and whether or not they are more interesting, less interesting, longer, shorter, and so on. So that's what this paper does. So there's the implicit assumption, which you need to believe in order to believe anything in this paper, is that AlphaZero actually has this ability. There is pretty good evidence that it does, because AlphaZero can solve classical chess and Go and Shogi and a bunch of other board games, all with the same hyperparameters. It can solve them such that it is easily at superhuman power. But you need to recognize that this is an assumption. So what is AlphaZero? If you don't know what AlphaZero is a reinforcement learning algorithm, but not in the kind of base reinforcement learning sense. It is a reinforcement algorithm that has a planner included. What do I mean by this? So if you are let's consider the game tic-tac-toe. So AlphaZero for tic-tac-toe. In tic-tac-toe, you have this board, and you have a situation where, let's say, your opponent plays this, and now you're tasked of playing something. You wonder, should I play maybe here or here or here? Where should I play? So what you can do is you can train a reinforcement learning algorithm. You can do Q learning, whatnot. Okay, that will maybe work. What's better to do is you can plan. So in planning, what you want to do is you want to build a tree of possibilities. So we want to consider all your possibilities. And in this case, you have 8 possibilities. So we want to consider all the 8 possibilities. And I'm going to draw just some of them. So up here, you're going to consider the possibility that you place here. And here, you're going to consider the possibility that you place in a different spot right here. Okay, and you can see how this goes. So if you want to plan, and here you have your opponent has 7 possibilities, and here your opponent also has 7 possibilities, and so on. So you get this entire tree of play. But if you could do that, and if you could do that to the end, then you could easily simply choose the path here where you win. Okay, where no matter what your opponent does, you win. You can find such a path if it is possible at all to win, which it is not in tic-tac-toe, right? If everyone plays optimally, it results in a draw. But let's say you could win. You could choose the path that gives you the best result, and that's it. There's no learning involved, okay? So AlphaZero works with a planner, and planners usually construct a tree. So in an abstract way, you are in a situation and you consider all your options, and with all your options, you consider again all your options and so on, and you do a tree search. Now, this tree in tic-tac-toe, it's already huge, as you can see. In something like chess, it is way, way huger, okay? And therefore, it's not possible to actually search the entire tree, because you need to consider every single possible future situation from the board position where you're in, right? This here is the board position where you're in, and this is the future, the entire future of the game. So every single possibility. So AlphaZero uses this thing called a Monte Carlo tree search. It has several components. So its first component, and right here, they have a description, and it's very short. AlphaZero, this is AlphaZero. This is what it does. It's like, this is almost comically short. So what you do is you put your state. So S is your state, okay? S is, it's the board as you have it right now, okay? This here, this is S. Okay, you put this into a neural network, and the neural network gives you 2 things. First of all, it gives you P and V. So that's the second thing. So V will simply give you a number. V will tell you that this thing right here is about a plus 0.5. maybe. So it says, so +1 is winning and -1 is losing. And this is called the value. So maybe it says, well, this position, I'm going to expect you to win roughly 75% of the time, right? Which in expectation would be a value of positive 0.5 here, because 75% of the time you win and the rest you lose. Let's say there is no draw in tic-tac-toe. So there's this value function, and the second thing is this p, and the p is a policy function. So the p will, and I've drawn this a little bit, maybe not super duper too large, but the p will tell you for every possible move you could make, which one should you consider even, okay? So maybe it assigns this here a 0.3, and this here a 0.4, but this here is like a 0.0001, and so on. So for every possible move that you could do, it will assign a number, and it's a distribution, so these numbers add up to 1, but that's not important. It tells you which moves you should even consider going forward, right? So P in this case is a distribution over the next moves, and with those two things together, we can reduce our tree search quite a bit. So now, instead of expanding all the tree, let's go back to the tree right here, you can ask your P, hey P, which one of these three should I even consider? And maybe P says you should only consider those two, okay? And then you go down, and again, you ask your P, hey P, which one should you consider? And P maybe says, well, here you should consider those two, here you should only consider this one. And this tree over here, we've already discarded this from the beginning, okay? So this P right here, it guides your search. It tells you at each point which moves should you consider. And this, as you can see, reduces your tree dramatically. In fact, what AlphaZero does is it simply says you have 1 second of time. Now expand as much as you can in this tree, given this 1 second of time budget. And the second thing is the value. So what you would have to do expanding the tree is always to go to the end, right? So you always go to the end, where at the end you have a fully filled board. I don't know, here X, da-da. So you consider every possible situation. Okay, here maybe this player wins, as you can see. You always have to go to the end, but in our case, we don't want to always go to the end. We'd rather explore more into like more branches than always go to the end. And this is where the value comes in. So at some point you simply say, now I'm deep enough, and now I'm going to ask my value V. Now there are slight differences with respect to AlphaGo and AlphaZero and so on, but they all have in common that they estimate the value of the intermediate nodes using this V model from over here. I have V was green. So they use this V model from over here to estimate at a certain depth. So V learns to look into the future, so everything that can happen from here, and it estimates, and it says, well, from here you maybe have a 0.5 value, or maybe a negative 0.7, and so on. So V learns to assign these values to situations, to states, which are these nodes right here, and P learns to suggest things to expand, right? That's AlphaZero. And then at the end, if you've expanded the tree enough and estimated well, then you have a pretty good idea what's going to happen in each of the branches that you considered, right? In each of these branches, you look into the future. Here you look into the future, here you look into the future by doing this PV play. And after 1 second, after you've done, a couple of 100 or 1,000 or however many looks into the future, then you have a pretty good idea for each of the top level actions, what's going to happen in the future, and you can simply pick the one that has the best future for you, according to your own model. So that's what AlphaZero does. Note, so this is how you combine planning and neural networks. You want to do planning, but you can't because you can only go so deep. So you use neural networks to, first of all, reduce the number of branches you consider, because the neural network will tell you which ones are worthy to even look at. And second of all, you don't always have to plan to the end, because you can simply ask your neural network how much an intermediate state is worth in expectation. And this turns out to be pretty good. Why don't we do this for every single problem? Well, for this we do need a simulator. So you may recognize that right here I said we consider all the possible actions that we have, and for each action we know exactly what's going to happen. This is only possible like in a board game. It's not even possible in like a board game where you have a die to roll or a card to draw. Anything that is random, there is a way to include this right here, but in this simple formulation, we need to know exactly with 100% certainty what is going to happen if we take a particular action. So this is only really applicable for the types of full information board games where we can write simulators that are pretty fast, right? And even then, even though chess, has lots of available actions and complications, it's nowhere near the complexity of like let's say a modern video game or the real world is completely out of scope for now for these types of things. All right, so that was AlphaZero, which builds on AlphaGo, of course, and the rules of chess that we're going to consider using AlphaZero are the following. So there's no castling for 10 moves. Pawns can only move by 1 square. Forcing a stalemate is a win rather than a draw. So you may note this in chess, if you do not checkmate the opponent's king, but only put the king in a situation where it cannot move, that's considered a draw. And I think even in the chess community, some people want to consider this a win. There is torpedo, where pawns can move by 1 or 2 squares anywhere on the board. And semi-torpedo, where it's the same but only from the second and the third rank. Pawn back, where pawns can move backwards, and pawn sideways, where pawns can move laterally by 1 squares, but captures are unchanged, diagonally upwards. And there is self-capture, where it's possible to capture one's own pieces. So there are slight details here with respect to the 50-move rule and so on. But if you don't play chess, simply consider these are changes, in a lot of cases, minor changes to the chess rules that make the new rules either a superset or a subset of the original rules, but they are going to have quite some changes for the play, and we're going to look at what happens. So that's the entire research setup, as you've seen. It's AlphaZero applied to these new rule sets, and under the assumption that AlphaZero will become master at these games, which we can't verify. We can verify in chess because, right, AlphaZero can beat people that have trained chess for all their life. We can't verify it here. So again, this is an assumption. So the first thing I want to look at here, and this is going to play a little bit into my criticism of this paper. It's a pretty cool paper, but I do have some concerns right here, is the following charts. So we don't consider how you train AlphaZero. Let's just say you can train it, to whatever, pretty good performance. Here is how they evaluate. So they evaluate for each variant, they do 10,000 games played at 1 second per move for each different chess variant. So if you remember, as we do our tree search, right, we expand the tree according to our P and we estimate the values according to our V. And we do this for 1 second in this first thing. So in 1 second, maybe this here is the tree. So we have some sort of an understanding of what's going to happen in the future. You can imagine if we have more time, then we can expand this tree more and get a much more accurate picture of what happens in the future. Okay, so they do 10,000 games at 1 second per move, but they also, in addition to 1,000 games played at 1 minute per move. So there's 60 times more time, and you can imagine that will add quite a number of nodes here. And if your P and V would be perfect, then it wouldn't matter as much how much time you have, as long as you sort of have enough time. But since they're not going to be perfect, since they're only neural networks, they're not God or Schmidhuber, they cannot extremely accurately predict the future. So this planning, the more you plan, the more you actually look into the future, the bigger your tree becomes, the better moves you make. So on the left, you see the distributions of wins, losses, and draws for 1 second per move, and on the right for 1 minute per move. So both white and black pieces here are played by AlphaZero. So it's not AlphaZero against something else. This is playing against itself. And you can see in classic chess, it's quite saddening actually, that this game, which is so famous, you can see that of 10,000 plays, 8,820 end in a draw, which means that if both players are super duper good and play against each other, it most likely is going to be a draw. And this, I think, is the criticism even in human chess, is that it's not really a decisive game, in that it ends a lot of times in a draw. So one of the motivations here would be, can we find a rule set that is maybe more decisive? So that's one of the investigations they do in the paper. But you can see that there are actually, so if you consider this torpedo chess right here, it is more decisive, as you can see, in more times either white or black wins right here. And there are others which are even less decisive, like pawn back. So when pawns can move back, then players may just camp. They move a pawn forward and move it back again, and that will lead to a lot of closed plays and so on. Whereas torpedo makes you move much faster. You can advance your pawns much faster, and that will probably lead to the end much faster. So if you consider this on the right, so what changed? The rules didn't change. AlphaZero didn't change. It simply changed that we now let AlphaZero think for longer. And you can see that the decisiveness reduces dramatically. So whereas 88% resulted in a draw with 1 second per move, now 98% result in a draw with 1 minute per move. And this is a trend throughout these games. And that's also what they say in the text. It is to assume that if you let AlphaZero plan for even longer, that this trend will continue. And ultimately, whatever rule set you make, the result is going to be a draw. If two, let's say, perfect players play against each other, which is a bit saddening, right? Because that ultimately means that all of these rules aren't decisive. They're only decisive due to the fact that either one or the other players is way better, or that in general that they are not perfect. Which is an appeal of a game, but there are certainly games that are decisive, even though both players are pretty high level. I mean, think of every competitive video game. So that's a bit of my criticism. All of this needs to be analyzed in the background that what's actually happening here is that we're dealing with imperfect decision making due to a limit in resources. Okay, and this assumption now is already a little bit invalid, right? The assumption we made at the beginning, why I pointed this out, is that AlphaZero can solve these games, let's say, to perfection. And here, when we analyze the decisiveness and so on, it seems to be purely or largely a factor of how much time AlphaZero has to think about the moves. And these two things, to me, they don't really go together, because we don't know if for a different rule set, the training is harder or might take longer and so on, or that this exact 1 second makes a difference or not. It's just there are so many variables here, and when you're dealing with, let's say, imperfect systems that are not trained to the end or evaluated in their full potential, you're always dealing with the fact that you stopped each thing at some intermediate point, and where that intermediate point is can influence the results drastically. Now here it seems at least the ordering isn't changed by much, but this is one criticism. The other criticism here that I would have, again, is the fact that if you consider something like Torpedo, where you can move much, much faster, then yes, of course, let's say, I don't know, is it more interesting? That's the question right here. So they look at a lot of things like decisiveness, diversity, and so on, but the question is it more or less interesting to play? And I think that's what humans are really after, and they're sort of trying to find proxies to this. I would argue if you play something like Torpedo, the game's maybe much faster, and so you get to the end faster, but also maybe it might not be as interesting, even though it's faster, because the complexity is less. And with respect to the decisiveness here, so if you have a game that's faster, you also need to take this into account, because here is another thing that is sort of an arbitrary choice. As moves are determined in a deterministic fashion given the same condition, diversity was enforced by sampling the first 20 plies in each game proportional to their MCTS visit count. So what does that mean? That means that if you run AlphaZero on the same situation, on the same on the same board position, it will always come up with the same move, except for parallelism, inconsistencies, and so on. But it will, in a lot of times, it will come up with the same move. So how do you play 10,000 games? Because you can just play one game, because each game will be the same, because you simply tell AlphaZero, give me your best move, right? So it will just play its optimal strategy, and all the games will be exactly the same. So there's no reason why these should come out different. So they enforce diversity by saying, okay, in the first 20 moves of a game, we don't actually take the best move, right? Usually you have this distribution. At the end of the tree search, you have a distribution where you say, okay, this move right here is clearly the best move. I'm going to play this. However, if this is one of the first 20 moves of the game, they say, no, we need a bit of diversity, so we're going to sample according to this distribution rather than just play the best one. Now, this number 20, it's just sort of decided arbitrary, right? And if you consider something like Torpedo, it's a faster game. So you're faster in opening, faster in mid-game, you're faster to the end game maybe. Even though they say, well, the game length isn't affected this much, it could just be that you're faster in a situation where you're kind of forced to do certain moves. And maybe the difference in decisiveness here is simply a result of the combination of the faster moves in Torpedo together with the fact that they just keep the 20 plies for each game. Again, this is something that you need to consider when analyzing these results right here. And there are a number of these choices right here, like the 1 second or 1 minute per move. We sample for the first 20 plies before we play the max move. That where I think the results of the study right here, they have rather limited interpretability, if you ask me, because of these choices. Now, of course, the results are quite plausible, believable, and the idea is really cool to explore these rule sets, but this is just my criticism right here. So we'll go through the rest of the results pretty quickly, because a lot of people aren't chess enthusiasts, and we'll just pick out kind of the core messages that the paper is trying to get across. So here the table again with respect to decisiveness, and you can see even for classic chess, it's white has a 50. This is the empirical score for white under different game conditions. So 50.8% means most of the time it's a draw. So white wins with a probability of 50.8. Most of the time it's a draw. And you see even like the most decisive variant, torpedo, right here is a 54% only. So they analyze different defenses and how the decisiveness is with respect to different defenses that are not really popular under classical chess. And the results are interesting if you play chess, but I would say they're kind of okay if you do not play chess, because they consider individual moves and so on. What is an interesting part is this right here, where they look at one move that in classical chess, so e4 is a very popular opening, where you move your e pawn twice for white, and nf3 is not a super popular opening. And here they compare this in classic chess and in no castling chess. So this thing right here is a histogram, and the histogram shows you the log probability of opening sequences when you play the individual moves. So what does this mean? Right here, if you play e4, then the distribution is something like this, which means that you have some sequences that have no entropy at all, which means that once you play e4 and maybe one move more, then it's almost determined what you have to do according to AlphaZero. You have like no choice except play these few next moves. However, if you play nf3, then AlphaZero says, look, this distribution is much more to the right, which means that you have a lot more options here. Now again, this could be because the move is actually less decisive, because the move leads to more balanced, more interesting situations where you can continue, however, with many choices. It could also be because it's simply AlphaZero simply doesn't know as well what to do, because it leads to more complicated games, and you give each move 1 minute to evaluate. AlphaZero might just not be as good in those situations because it leads to more complicated situations. If it could search for longer, maybe this distribution would shift over here just as well. Again, we don't know, because you only give this 1 second or 1 minute each time for both. And again, this goes under the assumption of AlphaZero is this perfect player. However, back to what they want to say here, if you do this in no castling chess, you can see that this spike right here are all these Berlin defense variants, and castling, this OO right here, is a big part of that line. If you do this in no castling chess, you can see that these two moves, now the histograms overlap much more, which means that, and in fact you can see in this number of possible moves right here, that they come closer together. So not only does the blue shift to the right, the orange actually shifts to the left, and it basically means that whether you open with e4 or knight f3, you are going to have about the same complexity of game, the same number of moves available to you going from there. As you can see right here, these lines are the moves available for white and black under the different rule sets. So in E4, here, especially as black, you do not have many moves available, as white a little bit more, but also not more, whereas in no castling you do. So again, small rule change, big effect on the possible moves that you can consider. And this is the type of information that you would want to have when you design a game. And they allude to this also at the end here in their conclusions. So the last thing is they also compare the material values of the pieces here in the different rule sets, as you might imagine. So some pieces become much more or less valuable. I find it particularly interesting that if you do something like pawn sideways, or then where the pawns are much more powerful, of course, all the other pieces drop in value. Again, these results are pretty plausible, so I don't want to trash the paper right here, because it seems like the results are, as I say, plausible and can give some cool insights. So the chess master also gives his opinions on these different strategies that AlphaZero comes up with for the different rules, and let's go through the conclusions real quickly. So they say, assessing the consequences of rule changes in the game design process demonstrated on chess, where we've trained AlphaZero to evaluate 9 different variants representing atomic changes to the rules of the game. Training AlphaZero model on these rules changes helps us effectively simulate decades of human play in a matter of hours and answer the what-if question, what the play would potentially look like under developed theory in each chess variant. We believe that a similar approach could be used for auto-balancing game mechanics in other types of games, including computer games, in cases when a sufficiently performant reinforcement learning system is available. And yes, the application here would be for something like this. If you design a new game, then you want to know what you have some choice with how you can make the rules, and you don't want to let humans become really good at each of the rules and then compare. You can simply give this to the algorithm, and the algorithm will tell you what kind of plays result from each rule set, and then you can choose the one that you find most interesting or most maybe commercially viable and whatnot. I actually see this bigger than just games, and this alludes a bit to the Salesforce paper on this AI economist. I think we can let AI, tell us what happens if we change, for example, things like tax policy or any sort of policy. I know humanity is very complex to model and so on, and you're never going to have a perfect simulator, which probably makes AlphaZero not good. But in limited situations, like maybe also stock trading rules and so on, you could definitely have situations where the rule set is too complicated to solve analytically, but you could give it to an RL algorithm and see what happens, and whether or not you like the outcome, and whether or not there are any obvious exploits that you did not see. So this I find it's a pretty cool approach, and we should think of this in the future as we build systems that have rules in whatever capacity, be this games or policy. So they say, okay, yada, yada, yada. We showed that there are several chess variants among those considering the study that are even more decisive than classical chess, meaning torpedo chess, semi-torpedo chess, no castling chess, and stalemate equals win chess. We quantified a rising diversity of opening play and the intersection of opening trees between chess variations, showing how different the opening theory is for each of the rule changes. Yeah, this diversity of opening play it really rests on this assumption that AlphaZero is a good player, and sort of an equally good player in all of these variants, right? Because if it's worse in a variant, it might not be as sure about the moves, and that would just look like, oh, you have many possibilities, but in fact AlphaZero is just worse at it, and it doesn't know. So they also look at the intersection of opening trees, like if you change a rule, how does this change how does this change the initial game? So a lot of these grandmasters, they learn by heart all of these opening trees, the initial moves of a game. How much would they have to relearn? There is a negative correlation between the overall opening diversity and decisiveness, as decisive variants likely require more precise play with fewer plausible choices per move. Again, this is one view, right? The other view is that there are rule sets that are just make it into a harder game, and then AlphaZero, given the same amount of compute, is a worse player, and therefore it can't play as well. Therefore, the games are less decisive, and also the opening diversity is higher because it doesn't know. The game could be as decisive. It might just be an effect of AlphaZero. For each of the chess variants, we estimated yada yada yada. Okay. No castling chess, being the first variant that we analyzed, has already been tried in an experimental Blitz Grandmaster tournament in Chennai, as well as a couple of longer Grandmaster games. Our assessment suggests that several of the assessed chess variants might be quite appealing to interested players, and we hope that this study will prove to be a valuable resource for the wider chess community. I don't know, is the chess community flourishing or going under recently? Because it seems to me like once a game is solved that hard by computers, I mean, it's still fun, but I guess Counter-Strike is also solved by bots real hard. It's still impressive when humans play or so. I don't know. All of this is, again, if you're into chess, look into this paper. They have a lot of really interesting results that are not interesting to go into for the general community, but I believe this should give you a good impression of what you could do if you design a system that is built on rules. All right, so this was it for this paper. I hope you enjoyed this. If you liked it, leave a comment, tell me what you think, and I'll see you next time. Bye-bye.